Okay, let's continue and do part B of this problem. So we've done part A. Now part B. Now we need to actually use this formula for heat and specific heat capacity to work out how much water was added. So I'm just going to scroll down, set this up. We need the formula. Now the key thing to note here is that the energy that is gained by the cold water to increase the temperature of the cold water is the same energy that is lost by the hot water, because remember there is energy transfer which goes from hot to cold. So we are treating, hold up, we're treating the, in our system we have hot water and energy is transferred to the cold water. Oops. Sorry, I don't know what I pressed and now it's not responding. Okay, fixed it. Cold water. Energy is transferred from hot to cold water. So this, the hot water, loses energy and cold gains energy. But the loss has to be equal to the gain. So if hot water loses energy, then we can say, well, it's in the form of heat, so it loses heat energy. Then delta Q of hot water has to equal to the gain, the change in heat energy of cold water. Alright, this is just the mathematical expression of what we agreed here, because the energy didn't come from nowhere, as you know. Energy came from the hot water into the cold water, and all this is our whole system. Oh. This is our system, and it's isolated from the external environment, so no energy escapes from this system, theoretically. So it's an assumption that we're making. Now, we know that the size of these two numbers, remember the units here are joules because it's energy, heat energy, these two numbers must be equal. But in physics, the sign is also really important. So I want you to think about whether these two figures, these two numbers, should have the same sign. And if not, why not? So pause the video and have a think about that. Now, I hope you've had a think about that. And coming back to the word equation, to what's actually happening physically. The hot water loses energy, and the cold water gains energy. So these are different things. I mean, the amount of energy that is transferred, the amount of energy is the same because it's just a transfer of energy. So we have to differentiate between the loss and the gain by saying if system loses energy, it has to be negative. So the cold water gains energy, so the change here is positive because, you know, the energy in this cold water has increased. Energy of the hot water has decreased, so therefore we've got a positive change for the cold water because therefore it increases in temperature, and we've got a negative change for the hot water. and therefore the hot water cools down, decreases in temperature because it loses heat. So this is I want you to stop here and really try to understand why I've done this and what's happened. And if you don't, then post a question in the discussion forum. So I'm going to do a little bit of a branch off here and explain this in general. That in general, there is a generalization for this, which is in the textbook, in work example 1.2. And basically, this is an extension or an application of the law of conservation of energy. Because all it says is that change in energy or the heat gained by a hot object has to be equal to the heat that's lost by a cold object. So heat gain is equal to heat loss, which should make sense in the context of the law of conservation of energy, the first law of thermodynamics, because this is an example of energy transfer and a mathematical way of expressing energy transfer. So if you have two objects that are brought into contact, whether they're liquid, solid, or gas, then the amount of energy that is lost by the hot object has to equal to the amount of energy gained by the cold object. And depending on the question, you have to be careful with the signs. Like I said, usually the hot object will always lose energy, so you might need to put in a negative here. Now going back to our question, where we have already put in the negative sign, let's substitute in the relationship that we know between heat and specific heat capacity. So, sorry, my computer's really laggy at the moment. Specific heat capacity. Okay. So on the left hand side we have negative mass of the hot water times C specific. On the right hand side we should have a similar expression that says, which is this equation here, except for the cold water. So we have mass of cold water multiplied by the specific heat capacity of water multiplied by the change in temperature of the cold water. So there's two ways to go about this. We could rearrange the equation first for mass of the hot water, which is what we want. We can make that the subject and then substitute in the numbers that we know, or we could substitute the numbers in first and then rearrange. So I prefer to rearrange first and then substitute in numbers, because otherwise you get this messy expression of long or large numbers. So we want the mass of the hot water, which tells us how much hot water was added. We know the change in temperature of the hot water. We know the mass of the cold water, which is the 53 liters, that's already there. And we know the change in temperature of the cold water. So let's rearrange this and make mass of the hot water the subject. Okay, we want to get rid of this C times delta T part, so we have to divide both sides by C by C times delta T. T, temperature change of hot water. Same on the right hand side. I'm not going to write it because it's really laggy, so I'm going to just go straight to the next step. And then you get left with mass of the hot water negative sign is still there, of course. We haven't done anything with that. And the other side, the right hand side, is going to look like this expression on the top, mass of the cold water times specific heat capacity times delta change in temperature of the cold water, all over what we've divided by. So C again, delta temperature of the hot water. Okay, now we've got a formula that we can just substitute what we know into, and then we should get out the mass of the hot water. But first we can do some simplification, because we see in the top and bottom we have C. And remember what C stands for, the specific heat capacity. And since, you know, hot water and cold water should have, or they do have, the same specific heat capacity, then these cancel out because it's the same number on the top and bottom. So we are just left with the mass of cold water and these temperatures here. So writing this out, just move this up. What happened here? Writing this out, we have mass of the cold water. That's 53 liters, so 53 kilograms. Multiplied by change in temperature. So this is the cold water. So the final temperature of the cold water, remember, change in temperature means final temperature, take away the initial temperature. So the difference between the final temperature and the initial temperature, which was the temperature it started at. So the final temperature is 41 degrees, because that's what we want the bath temperature to be, minus 23 degrees, temperature that the water was at. And on the bottom we have the final temperature of the water, which is 41 degrees. So the final temperatures should be the same, because now they're mixed together. (41 degrees) subtract the initial temperature, which was 68 degrees, hot water tap. 68 degrees, hello.